Welcome back, everybody, to your second lesson for exponentials, exponential relations, which basically is just how exponentials look algebraically as an equation and how their graphs look and compare, and some other different formats like table of values. Goals, we're going to learn how to graph, or at least what a graph looks like, and be able to recognize exponential relations looking at the equation, graph, or table of values. So the exponential relation is any relation that can be represented by the equation, like it is written below. As a quick review from your first lesson, that A is the base. So this says it has to be a positive number. So we're not going to deal with anything that has a negative number because as the base, because it behaves differently. Does not equal 1. And then remember, your x is your exponent. So the key to take away from this is anything that's exponential actually has the letter or variable as the exponent. The ratios of consecutive y values are constant. And we're going to take a look at a specific example explaining this in the next slide. We're going to do something with the table of values. So that has to do with a table of values. Now these two graphs on the bottom, we have two different types of exponential relations. One is growth and one is decay. As you go left to right, if your graph is increasing, so if your relation's getting higher as you go left to right, it is considered exponential growth. So if you're looking at both of those, which one is increasing as you go left to right? The one on the left. So this right here is exponential growth. As you go left to right, if it's decreasing, that's exponential decay. The one on the right, as you go left to right, is decreasing. That's called exponential decay. When you're looking at an equation for the growth, so for the growth, the base has to be greater than 1. For decay, so these ones, the base has to be between 0 and 1. Not including 0 and 1 though. So between 0 and 1, which basically means you're going to end up with either a fraction or a decimal. So like 0.5 or 1/3, anything like that. So growth increases as you go left to right, decay decreases as you go left to right. For growth, the base has to be bigger than 1. For decay, the base has to be between 0 and 1. So not a whole number, just a fraction or a decimal. Our first example, make a scatter plot of the data. Make a scatter plot just means make a graph. I'm going to show you in the next slide what the graph should look like. You're welcome to try this on your own with pencil and paper. And then we're going to describe the graph. So we'll save that for later. What I really care about is you copying down this table. So if you need time to copy down this table, pause it, then start it back up again once you have it copied. So we're going to calculate the ratios. Now, in grade 9 and 10, you do first differences. And we did first differences in this course at the beginning as well. But you do differences. So you start at the bottom, work your way up, and you subtract. And if the first differences are equal, it's linear. And then when we did quadratics at the beginning of this course, If you got the first differences not equal, you did it a second time, and if they were equal, then you would say that it was quadratic. For exponential relationships, you don't subtract. You find the ratio, and ratio just means fraction or divide. So when you're doing ratios, really, that means you're dividing. So what we're going to do is we're still going to start at the bottom and work our way up. So you make this kind of like accordion zigzag shape is what I like to make. So start at the bottom. You make this hitting all your numbers. And I like to put an arrow on the end to show you that we went from the bottom to the top. But instead of subtracting like we did at the beginning of the course, we're going to divide. And you're going to see what happens. So if you take out your calculator and do 46 divided by 162, you should get 3. The next one, 162 divided by 54. So remember we did this, so start here. This divided by this is 3. This divided by this, you get 3 again. 54 divided by 18, 3 again. 18 divided by 6, 3. 6 divided by 2, 3. What you notice is they are all the same. With them being all the same, we know that it is exponential. So we're going to say, therefore, the relationship is exponential. And then you always want to say why to show me that you know. You didn't just guess. So the relationship is exponential because ratios are equal. They're all 3. I can guarantee you this is going to be a CCA or exam question, and more than likely it's going to show up on your test. Here's a table of values. Tell me if it's exponential or not. Do the division, and you're going to say it's exponential because the ratios are equal. Or if you didn't get 3 or the same number for all of them, then it's not exponential. And that's because the ratios were not equal. When it comes time for your exam, or CCA, you're going to have to do first differences to prove that it's linear, then do second differences to prove if it's quadratic. And if neither of those two end up being equal, you'll do ratios. So that'll be like your third test. And if they end up being equal, you know it's exponential. If not, then it's not linear, it's not a quadratic, it's not exponential, it's none of the ones that we've done for this course. Is this exponential growth or decay? So that's part C. This is actually growth. Now there's 2 ways you could tell me it's growth. You could tell me it's growth because as your x numbers are increasing, so as these are increasing, your y values are also increasing, 2 to 6 to 18, and so on. The other way you could tell me is because our constant ratio was 3. And if that number is a whole number, positive whole number, then we know that because we got 3, it's growth. Again, I can't stress this enough, you are going to see this type of question again. Using a table of values, either subtract or do the ratios to prove if it's exponential or linear or quadratic. Now coming back, make a scatter plot. You're going to notice it looks like this. And when you're making graphs of exponentials, you don't connect them with straight lines. So don't line those all up and make like a straight line like you're connecting the dots. You want to try to make a smooth curve. And we want to put an arrow on the end, on both sides actually. And remember, when you are graphing exponentials, they are either going to look like this, or they're going to look like this. This is growth. This is decay. Now clearly this is growth because as you go from left to right, you can see you're increasing and you're not decreasing. And anything that's exponential too, you're going to notice that these little gaps, so it's a little harder to see, but that jump, and then that jump, and then that jump. So you can see that these jumps, these spaces from here to here, and here to here, and then from here to here, they keep getting bigger and bigger. So anything that has an exponential increase, it eventually starts to explode. And same thing with decay. It starts to explode at first, and then it kind of tapers off a little bit. So basically, I know you might be thinking maybe they look like half parabolas. I don't mind that thought process. They're going to make either something like this or something like this, kind of like a half curve, if you want to think about it like that. Our next example, complete the table and graph each using Desmos. So if you want to, if you have Desmos loaded up on your laptop or on your phone, you could type in those 4 equations and graph them on the same graph, and then we're going to talk about them. We're also going to get some practice using our calculator and using our exponent rules to come up with some of these values. So the first thing we're going to do this column first. So 2 to the x. So really, I'll do all the steps for this first one, and then after that, you can do it on your own, and I will take up the solutions. So this means 2, and again, it's not 2 times x. X is the exponent, so it's 2 to the negative 2. Now you could enter that into your calculator, but practicing your exponent laws, you should remember if you have a negative exponent, you flip the base. So, and remember that's really written over 1, so this is 1/2, and then make your exponent positive. 1 squared is 1 and 2 squared is 4, so that equals a quarter. Same thing here, 2 to the negative 1, flip it, 1/2, make your exponent positive, that just equals 1/2. Anything to the power of 0, what is it? Shout it out, 1. 2 to the power of 1, you can use your calculator, is 2. And 2 squared is 4. So if that makes sense, follow those kind of steps we did. And then if you want, you can pause it and go through the rest of these and complete them. If not, I'm going to take up the final answer. So this would be 3 to the negative 2, which becomes 1/9. This would be 3 to the negative 1, which becomes 1/3. This is 1, right? 3 to the 0. 3 to the 1 is 3. 3 squared is 9. Now for the next one, I'm going to take even more steps away, and we'll come up with the right answers. So this 1/2, so you can enter as 1/2 or you can enter as 0.5. I would encourage you to use the ABC button and enter as 1/2. And don't forget to put the brackets in just like you see them. 1/2 to the negative 2 is 4. The next one's 2. This is 1. 1/2. 1/4. And then the last one, 9, 3, 1, 1/3, and 1/9. There's some things you should notice when you're looking at each individual column. So let's say we're looking at this one. You're going to notice that we got 9, 1/9. So on opposite ends of the spectrum, like when we had negative 2 as x and positive 2 as x, they're just kind of flipped of each other. 9, 1/9, 9, 1/9, 3, 1/3, 1. And that pattern follows 4, 1/4, 2, 1/2, 1. And same thing all the way across. And at 0, something happens. So if we look across, regardless of what the base was, they all have the exact same value. They all have 1. Moving to the graph, if you didn't graph it on Desmos, that's okay. This is kind of what it would look like if you graphed. And definitely copy those down. And once you have those copied down, we're going to write some things, some summary things about these. So the first thing, let's label these. The green one. The green one was 3 to the x, and the blue one was 2 to the x. And the yellow one was 1 1/3 to the x, and the red one was 1/2 to the x. The 3 to the x and the 2 to the x were growth. So the growth ones were the 3 to the x and the 2 to the x. And the decay ones were 1/3 to the x and 1/2 to the x. And that fits our definition. For growth, anything that has a base bigger than 1, which 3 and 2 are bigger than 1, it increases as you go left to right. Decay is the opposite. If you have a number between 0 and 1, which 1/2 is 0.5 and 1/3 0.33, repeated, those are exponential decay. Which one would you say, so if we look at the growth ones, which one would you say is steeper? I think we could all, using common sense and just looking at it with our eyes, the green one is steeper. It's 3 to the x. It grows exponentially quicker. So that's an important thing here that we're going to write. So the larger the base for growth, the steeper the graph. Or in other words, the quicker it grows, the bigger that gap gets, the faster it kind of explodes into very, very large numbers. If you look over on the decay side, so the 1/3 and 1/2, actually the opposite is true. So if I asked you which one's steeper, hopefully you would say the yellow one. And that goes with the 1/3. Well, 1/3 is actually smaller than 1/2, right? 1/3 is, if decimals make more sense to you, 1/3 is basically 0.33333, and 1/2 is 0.5. 0.5 is bigger. It's a bigger number than 0.333, but it's actually less steep. So the opposite holds true for decay. So for decay, the smaller the base, and again this is for decay, the steeper the decay, or the steeper the graph. So again, if it's growth, the bigger the base, the steeper it is, the faster it grows. For decay, the smaller the base, and again, 1/3 is smaller than 1/2. If I had you do like a quarter it would be smaller than 1/3 and 1/2, it would be even steeper. The smaller the base, the steeper the decline, or the more quick that it decays. So there's two important patterns from this. The next one, what point do they all go through? They all go through here. They all go through 1. As long as you haven't done any transformations to these graphs, they have a y-intercept of 1. And again, that's because anything to the power of 0 is 1. If we kept going, so if we kept extending these, so if I kept going this way with both these, and you can try as you may with your calculator, you will actually never get 0. You'll never even get a negative number. It'll keep getting smaller and smaller and smaller. So one other important thing, again, as long as there's been no transformations, an exponential graph can never beat 0 or negative. Again, as long as there's been no transformations to it. It'll keep getting closer and closer to the x-axis, but it'll never touch or cross it. And as like a bit of a bonus, I'm not going to ask you this, but if you want to know what that type of line is called, it's actually called an asymptote. But you don't have to worry about that. So those are the patterns you want to take away from making these graphs. The next thing I want to do, I want to make a summary chart, and this is going to be important for your workbook questions, for your test questions, for your CCA/exam questions and just for your general knowledge. So I'm going to make a summary comparing. So we're going to compare linear, quadratic, and exponential relations. So summary of, we'll say, course graphs. I know relations is kind of a fancy word, so we'll just stick with course graphs or equations that we used. And we did, well, we didn't do very much with it, but there's linear, quadratic, and exponential. And we want to compare them. So, like, how do they look as an equation? How do they look as a table of values? And how do they look as a graph? So let's start with the equation. Linear. Y equals mx plus b. Looks something like that. Quadratic. So quadratic has a squared in it. So x squared, remember, has to be the highest exponent on x. An exponential looks like this, which the letter, the x, is the exponent. So when you're looking at the equations, you can tell which one is which by if it just has an x in it, it's linear. If it has an x squared, and that's the highest, it's quadratic. And if x or some other letter is in the exponent, it's exponential. From a table of values, if it's linear, first differences are equal. If it's quadratic, second differences are equal. And we just learned if it's exponential, ratios, which we'll make a little note here, it means divide, are equal. From a graph, if it's linear, it makes a straight line. So it could be like that, could be like that, could be like that, or it could be like that. For a quadratic, it makes a parabola. So I guess we'll write this one. Self-explanatory, but makes a line. Parabola. Your two options for a parabola: opens up or opens down. Remember, this was a positive and this was a negative. Exponential doesn't have a fancy word to name it that we went over for this course, but it looks like that, or it looks like that. And this one is growth, and this one is decay. So again, that's a very good comparison chart of all the things you kind of need for the graphing model, the graphic models and equations that we focused on for this course. Linear, grade 9 and 10, we touched on it. Quadratic, we focused a lot of time on that to start the course, and then exponential, we're doing it right now. Again, very important things. Make sure you know that. You're probably going to see that again in the future. How can you look at the equation? Tell me what it is. How can you look at a table of values and do some things and tell me what it is? How could you look at a graph and be able to tell me what it is? There it is for you comparing everything. The last thing we're going to focus on for this lesson, we're going to get into some word problems. So Ontario's population can be modeled by this exponential relation. We know it's exponential because the letter, and it's not an x in this case, it's an n, the letter is the exponent. P is the population, n is the number of years. Now this is key, after 1996. So we're going to complete a table of values going from 0 to 40. What was Ontario's population in 1996? and what is the projected population in 2031, which is the last year this equation is thought to be valid. So I'll give you a second to copy that down, pause it, and then on the next slide I'm going to start answering these. So our solutions. I'm just going to rewrite the equation so I have it here. So P equals, and I think it was 11 million, and then it was 1.0112 to the exponent n. So the first thing I want you to do is make a table of values. So, and I said use n, p, and go from 0 to 40, but go up by tens. So 0, 10, 20, 30, 40. Now I want you to complete that. How do you complete that? Well, you put 0 in for n to start. So everyone take out their calculator, enter it just like you see it. So 11 million bracket 1.0112 close bracket, and then for n, the first n value we get is 0, put 0 in, and then hit equals. You should get 11 million. Now do it with 10. So enter your equation just like you see it, brackets and all, but then put 10 in. You should get 12,295,984. We'll go to one decimal place, 0.2. Now we can't have 0.2 of a person, so we would round to the nearest whole person, usually. Then 20. Put 20 in. Type it in your calculator. 13,744,656.9. Put 30 in. 15,364,007.6. And then last but not least, put in the 40. 17,174,144.9. And there's our table of values. What was Ontario's population in 1996? Do not put 1996 in for n. We're going to get an astronomical number. The key that we circled on the last slide was n is the number of years after 1996. Well, if it's asking you what the population was in 1996, how many years after is that? 0. It's not beyond 1996 at all. And we already have our value for that. So technically speaking, n, which is the number of years after 96, is 0. We haven't got past 96. So our answer to that, 11 million, 1996 population. C, what is the projected population in 2031? And that was B right there. The most common mistake, someone's going to enter 2031 for n. That is not the number of years since 1996. So to do these types of questions, our starting point, our point of reference is 1996. So what you want to do always first, figure out how many years are there between 1996 and 2031. How do you do that? Just subtract. So 2031 minus 1996 means 35, which means already we should be thinking, as a self-check, we should be getting a number in between 15 million and 17 million. But let's use our calculator. P equals 11 million, 1.0112. And we're not putting 2031 in for n, we're putting 35 because it's number of years since or after 1996. Enter that into your calculator, and hopefully you get the same thing as me, 16,243,881.7. That's right in between 15 and 17 where it should be. So we can make a safe assumption at least that we're probably pretty close to where we need to be. Whereas if we got something more than 17 million or less than 15 million, we either made a mistake in our table of values or we just made a mistake in the calculation we did. So that's it for talking about exponential relations. This was a little preview to a word problem. Your last lesson for the day, we are going to do the first half of our word problem lesson.